these are the equations we have. So then you are having this R11 is equal to A double dash plus A minus A dash plus A. So these are the equations we have written in the last lecture, but let me rewrite them here. So let's call this as 1, this as 2. Then you are having this R22 is equal to 1 by B minus 1 plus R by 2B, A dash by A minus B dash by B is equal to 0. Let's call this as 3. And R33, that's equal to R22 sine square theta is equal to 0. This is equation 4. Okay, so we'll solve equations 1, 2 and 3 constantly. And equation 4 is actually a restatement of equation 3 because it contains R22, so it is this thing multiplied by sine square theta. Okay, so it's a trivial thing. Now if you see the pattern in equation 1 and 2, so you are having A double dash with a minus sign divided by B. Here it is A double dash by A. Clear? So what I will do, I will multiply equation 1 by B by A. Okay, then add this equation 2 like this thing. So let me write B by A times equation 1, okay, plus equation 2. So what we will get? We will get something in this objective. Okay, what we will get? So it's minus A dash by R A, then minus B dash by R B, that's equal to 0. Only these two terms survive. Rest will cancel out. So what you will get? So it is simply A dash B, okay, plus B, okay, A B dash is equal to 0. So which implies that you partial R A B, because a dash means the differentiation with respect to R, okay, it gives me A B is equal to constant. Okay, so let's call that constant as alpha. Okay, alpha is our constant which we need to determine. Clear? Okay, so we are having this very equation. Clear? Any problem? Okay. So now if you look at this very equation, what you are having from this very equation, so it is something A dash by A is equal to minus B dash by B. Clear? So it is just simply a restatement of this. You divide this equation by A, or simply this thing. A dash by A is equal to minus B dash by B. Clear? So from this very equation. Okay. Now let's use this in equation 3rd. Okay. In equation 3rd, if you see, there is like this A dash by A. Clear? So I want to replace it by B dash by B. Okay. So let's write. So what is our R22? So therefore equation 3rd implies, what is that? 1 by B minus 1 plus R by 2B. So what is A dash by A? It is minus B dash by B. Then you are having minus B dash by B, that's equal to 0. This object. So what it gives me? So it is 1 minus B divided by B, like this thing. Okay, so minus, so it is twice, 2 and 2 will cancel, so it's simply R B dash by B, that's equal to 0. Okay, so what we get? So it implies, so it is 1 minus B is equal to R times B dash. Okay, so what that is? So I am having, sorry, it is B square. So it is B square, so it will be B, because you are having B into B, it is B square. Okay. So what is our B dash? So what is our B dash? Just tell me. Just tell me what is our B dash. So this is something R divided by B dB by dr. Clear? B dash is simply differentiation of B with respect to R. Clear? So now let's integrate it out. So I will write like this thing. dB divided by 1 minus B into B, that's equal to, okay, so you are having dr by R. So let's integrate it. So this gives me simply what it gives me. So this object is, if you see, it is simply 1 minus B plus 1 by B by partial fractions. Okay, 1 divided by 1 minus B in, is this partial fraction? So it is log minus log of 1 minus B, and this is plus log of B. So it is, so integration will be simply log of B by 1 minus B. So you can introduce a constant here. So let me write log of R by K, where K is the constant of integration. Okay, this we need to figure out what K is. So we are having two constants of integration, alpha and K. Clear? So you can see now, so it is simply B is equal to R by K into 1 minus B. Let's figure it out. So what you get? So you get, so which implies B into 1 plus R by K is equal to R by K. So what you get? So you get that B is equal to R by K divided by 1 plus R by K. So that's equal to 1 divided by 1 plus K by R. So this is our what? B of R. So what is our A of R? Okay, so what is B? Now let's calculate A. So A is equal to alpha by B. So what that is equal to? Alpha divided by 1 divided by 1 plus K by R. So how much is that? So it's simply alpha into 1 plus K by R. That is 1 minus 1. Okay? You got what, Mother? You know why it is minus 1? So it will come in the numerator. Okay. So this I can write as 1 plus K by R. Now let's write our, so we have figured out A and B. These were unknowns in our line element. Okay, so let's write the Schwarzschild math line element. So therefore our Schwarzschild this line element can be written as, so GS square is equal to E of R minus times A of R. So that's minus alpha into 1 plus K by R. Then you are having GT square plus, then you are having B of R. So what is B of R? So it is 1 plus K by R raised by. Okay, so let me put it this way in the usual fashion. So it is 1 divided by 1 K by R. So this is GR square. Clear? So it is this very object. Then what you are having? R square d theta square plus sine square theta d phi square. This is our Schwarzschild geometry. Clear? What is unknown here? What is unknown here? Alpha and K. So let's try to figure out what are alpha and K. Clear? So everybody got it? What I am trying to do? What I have done a simple analysis to figure out what A and B is. Okay. So what are the what these functions are? So let's try to figure out what this K and alpha is. Now let's take weak gravitational limit. So this is for the arbitrary gravitation, is it? Whether you are having the weak gravitation or the strong gravitation. So it is for completely for an arbitrary gravitation. Clear? So let's take the weak gravitational limit. Okay. Then this will help us to figure out. So let's take the weak gravitational limit. So in that case, if you remember in the V gravitational limit, the G00, the 00 element of the metric tensor, it goes as 1 plus 2 phi, where phi is the potential by c square. Clear? Is this true? So, or in other words, I can write this A of r by c square. Since A is the function multiplying by what? Dt square. Clear? So A is actually multiplying this thing. So that goes as 1 plus twice phi of r by c square. Now let's compare the two. So this is our G00 element. Clear? Is this G00 element? Or in other words, this is what objective? This objective. This is A by c square. So what is the actual, when you write in term, okay, line element, it's like this thing. Okay, sum A of r c square dt square plus dr square kind of thing. Okay, plus jz. Minus. So because this c square is multiplying dt square, clear? But if you see in this line element, I have no c square. So that means I can have A, if I, okay, in this very line element, I will divide this by c square, multiply this by c square. So that it is dimensionally correct. Clear? That's what I am saying here. A by c square tends to what? 1 plus 2 phi by c square. That is the weak gravitational limit. Okay? Okay, so now let's compare the two. What is our A of r? What is A of r? It's alpha times 1 plus k by r. What is our k? So therefore k is equal to 2 phi. Okay? Then what is alpha? Alpha is simply c square. You can check it from here. So if I put alpha equal to c square, so the dimensions of this are correct there. Okay. So now if I look at this object of, let's say I'm having the mass. Let's say my this spherical body has the mass m. So what is the potential therefore? So the potential is simply equal to minus gm by, it is potential. Okay? So let me use a constant, let me define minus, okay, so let's write therefore what this k is. It's minus twice gm, okay, by r. Okay, so therefore what is our line element? Tell me what is our line element. So we are done with it. So therefore ds square, it is equal to minus, so it's 1 minus gm by c square r, okay, c square dt square plus 1 divided by 1 minus gm by c square r, okay, dr square plus r square d theta square plus sine square theta d phi square. Clear? Anybody? Okay, so let me rewrite it in this way. Let me introduce a constant mu is equal to, so it is twice gm. Twice, k is twice gm. Let's write it. Gm by c square. Let's call gm by c square to be mu. So therefore, I am having ds square is equal to minus 1 divided by twice mu by r c square dt square plus 1 divided by 1 minus twice mu by r. Okay. Then you are having dr square plus r square d theta square sine square theta d square. Okay, so this is our general Schwarzschild metric. Okay, so what metric is diagonal now, is it? So you are having the G00 element what? 1 minus twice mu by r. What is G11 element? 1 divided by 1 minus twice mu by r. What is G22? R square, and G33 is r square sine square theta. Clear? So that means outside, so this is the, which region? Outside a spherical body. Okay, we are not inside. So we call this as the exterior solution. Got it? So in which region we are here? So we are actually in the region. Okay, so let me tell you. So you are having a spherical body, let's say. Okay, so this is our mass m. So we are here. So it is outside this very region. Okay, so actually, if you see, let's look at this. We'll be doing in detail in the next lectures when we will take the black holes. Okay, so if you look at this very metric element, this I mean line element. Now let's take if this 2 mu goes as r. Samajh? So you see from here what will happen to this very element? It becomes 0, but this is also 0. It's 1 divided by 0. It diverges. Clear? You can say there is actually a singularity, but it's an apparent singularity. It is not a singularity. Clear? So that means our line element, this very object is valid. This solution is valid up to which region? R greater than 2 mu. So if okay, so this very solution is valid for what? R greater than 2 mu. When I put R equal to 2 mu, R less than 2 mu, then this solution is not valid. We have to relook at this very solution. Although the line element will be the same thing, but we have to relook at the trajectories. We'll see it. Okay. Okay. So if you are having some body are carrying mass m, so let's say if it contracts by the radius r less than 2 mu, then it becomes what we call a black hole. So that will take later on. Okay. So there are two things to note in this very which we are going to take in detail later on. The first region is r equal to 2 mu. When the metric element, this line element diverges. Clear? When you take r equal to 2 mu, this object diverges. Clear? So much on. Now another is when you take r equal to 0. So we have to figure out which is actually the real singularity. Whether r equal to 2 mu is a real singularity or r equal to 0 is a real singularity. Okay? In this kind of thing. So it turns out to be r is equal to 0 is actual singularity. R equal to 2 mu is not a singularity. Okay? It is something apparent singularity. The reason being because we have chosen a set of coordinates. Okay? In one coordinate system, my element looks like this thing. I can make a coordinate transformation to remove this r equal to 2 mu singularity. So that means it's an apparent singularity. Okay? So much on. Okay, so you can think it in this way. Suppose if I give you a sphere and I want you to pick, let's say, some region from that very sphere. Think of a globe and I want you to pick some region from that globe. Okay? You cannot take all the maps or all the charts on that very globe simultaneously. You will be accessed to only a region of that very globe. When you try to look at the portion of the globe, that means you are accessing only a given portion. You are not accessing the entire globe. That means the coordinate system you are using to access your region has a limited value. That means if you want to get the maximum information out of the surface of that very globe, you need a different kind of coordinate system. Suppose if you look at a particular point, you don't look actually at the entire region of the globe. Got it? So this is this I will tell you in detail when we will take the black holes. What exactly is happening? You will see actually the fun with the coordinate systems when we will take the coordinate transforms. Clear? For the time being, we will say the geometry outside a massive body, okay, is like this thing. This describes our geometry because we are interested in the regions for r greater than 2 mu. So it suffices our discussion. Okay, we'll say, let's say, we'll think of a particle falling under gravity in this very region and try to figure out what kind of trajectory it follows. So we'll take those kind of notions here. Okay, so there is one important theorem, what we call the one important. You can take it as a remark or a corollary. So that's actually a theorem, what we call the Muzaffar theorem. So it says the space-time outside a spherically symmetric object is in general Schwarzschild. Okay, That means outside any arbitrary spherical body you take, okay, outside that body, the geometry is described by Schwarzschild geometry. Okay, got it? Okay, so that is actually the Birkhoff theorem. So this is the content of the Birkhoff theorem. Let's move beyond. If you have any question till now, just tell. Okay. So let's take. So everybody is written it. Any question? So all these derivations have gone now. Huh? So you should be, you should not worry. Now we are having simple derivations. Huh? We don't have to look at the tensors back. Huh? Everything comes with this very metric. All the physics what we have done is with this very metric. Okay. So let's take the gravitational redshift. Okay. So let's think of a gravitational redshift. That we have done already from the equivalence principle, is it? Is that true? So can anybody explain me gravitational redshift? Anybody? Once a better mask. What is gravitational redshift? This we have done already. Eh? Cross a fan, yeah. But you are the kid. So you pawn silicon. So fix it at some position. Eh? Okay, good. Sir. Who is Raj Shaskari? Who is Raj? Wait. Good. Okay. When is it? Gravitational redshift क्या है? मानो? पता? गैर कितना पड़ा? Both Windsor. कॉफी छुआ गैर मुस्रावन? कभी वन सचेशमिश हाँ आपने बोला ठीक है frequency, but that arises because of what? The gravitational field. Even if you are in the static gravitational field, if you are a stationary observer, so the gravitational field affects the frequency, okay, what you are detecting. Clear? So because of the gravitational time dilation. So let's try to figure it out from this Schwarzschild geometry, okay, because now the geometry is known to us. Clear? Okay, so let's think of, okay, so let me, suppose you are having some massive body, clear? So we are in this very region, huh? So let me take, so let's take this as, so this dotted line can be inside this, this very region, or it can be outside this thing. Let's call this as R equal to 2 mu. Huh? So this can be inside or this can be outside, okay? R equal to 2 mu. समझ आओ? So why we are in this very region, clear? So this is R greater than. We'll see later on. Huh? So if you calculate it for the Sun and Earth, this R equal to 2 mu, the Schwarzschild radius, we call this as a Schwarzschild radius. This exists within the object, clear? So let's calculate it for this, let's say Earth. So it will be inside the Earth. So if you calculate it for the Sun, it will be inside the Sun. If you calculate it for some massive body, let's say 10 solar mass object, clear? So it will be outside. So we are interested in the geometry here. Okay, R greater than 2 mu. Okay, so let's think of two observers which are stationary. Huh? Okay, let's say you are having in this very gravitational field, you are having an observer A here and you are having an observer B here. Or we will call this as, let's say this is an emitter. So this emits waves and this receives waves. Or let's say this emits a photon and this receives the photon. Clear? Samushama? So emission of a photon is an event and the reception of the photon is an event. So if they are fixed, I am saying these are what? The fixed observers. Two fixed observers. What I mean to say, let's say we are outside the sun here. Clear? So I am one of the observer. I am here. I am fixed. Okay. Let me sit stationary. Clear? So that means my r, theta, and phi coordinate are fixed. So because our metric is defined, line element is defined in the coordinate system p, r, theta, and phi. Clear? What I am fixing? R, theta, and phi, because I am at a fixed radius from the sun. Clear? And my theta is fixed. That means angle at which I am oriented with respect to the center of the sun, and phi as well, the this zenith. Clear? Similarly, let's take another observer which is also the fixed. Clear? Let's say that guy. Okay, he is fixed. Okay, so let's say I am sending a signal from here to that very observer. So he will receive, and we need to look at, okay, so first tell me what kind of geodesic it will follow. So when I am sending a signal from, let's say, from this point to this very point, so it will be a geodesic. Clear? Because it's a photon, so the geodesic has to be null geodesic. Time-like, if you are having a massive particle, that means you are having a time-like geodesic. Clear? We are interested only in time-like and null geodesics. Clear? Why time-like? Because when I throw a massive particle towards another person, so it will also move with velocity less than velocity of light. So that's why time-like. If I am, let's say, throwing a particle with more than velocity of light, that's a space-like. We are not interested in the space-like geodesic. Clear? We are only interested in the time-like and null geodesic. Since I am throwing a photon, it goes with the velocity of light. It's a null geodesic. Clear? Okay, and I will see what is the, because we are in a Schwarzschild geometry. Clear? Or we are in a background curved space-time. We need to look at what is the effect on the rate at which the signals are received by this receiver. Clear? So if the rate is same, let's say at the rate at which I am sending the signals, if it is the same at which they are being observed, it means there is no frequency shift. Clear? Okay, but we will see there, because of the gravitation here, there will be actually a frequency shift. Okay, if there arises this kind of frequency shift because of this gravitational field, such kind of frequency shift we call as a gravitational redshift, and this is purely because of gravitation. It's not the kind of the Doppler shift. Doppler shift is because between the moving observers. समझ आवा? You can have this gravitational redshift. Since I am considering only the fixed observers, you can consider the moving observers as well. समझ आवा? But we'll simplify our calculations to take only the fixed observers. Got it? Okay, so let me draw the space-time diagram. Okay, so let's say this is the observer 1. Clear? So this is our fixed emitter, I will call. Okay, so I am fixing, let's say r is the coordinate, theta is the theta coordinate, phi is the phi coordinate. Clear? So that means what is fixed? R, theta, and phi. Okay, so now let me consider the fixed this receiver. So let's write its fixed coordinates as r, r, theta, r, and phi. So let's have an event here. So let's say A is an event. So that means this event is what? You send a signal towards B. Got it? So it will go as a null geodesic. Let's put it as a dotted signal. So it is some B here. So I am sending a signal at a coordinate time TA. And let's say, okay, so let me write TE. TE is the coordinate time. It's not the fixed time. It's our coordinate time at which the signal is being sent. So then, because the coordinates of this very event are fixed, so let me write like this. Okay. Similarly, this will be received at the coordinate time. Let's say TR is the receiver time. Okay, and its coordinates are actually fixed. This R, theta, R, phi. Clear? So now after some time this will send another signal. Clear? So let's say, so I am having, let me write this as C. Yeah? So after some time TE plus delta TE. So this RE is because it's a stationary observer. So these coordinates will remain same, r, theta and phi. Clear? So it sends us again a signal towards this very point. So let's say you are having this event which is received at like this in delta here r theta r. Clear? Okay, so now let's look at the okay, so AC, A is an event, C is an event, AC line, this is a null geodesic, is it? So, so these are actually null geodesic, this is our null geodesic, and this is, so I have drawn them as actually the straight line, is it? It's not necessary to be straight line, is clear? Null geodesic means ds square is equal to what? ds square is equal to 0, ds square is equal to 0. Clear? Because in the curved space time, the trajectory of the photon is what? It's a curved line, and we have to look at the geodesic. That kind of, for photon, it's a null geodesic. So what is our this here? So I am having the Schwarzschild geometry. It's minus 1 minus twice mu by r c square dt square plus so let me write 1 minus twice mu by r raised power minus 1 dr square plus r square d theta square plus sine square theta d phi square. So this is equal to 0 because it's a null geodesic. Clear? Can I write it? Okay, now let's look at this very thing. So these are all our special coordinates. Clear? So these defines out, this is r, theta and phi. They are the special coordinates. Clear? So समझ आओ? Can I write them in this very fashion? So this I can put as g alpha beta. Okay, so let's write it as, then I am having some dx alpha, dx beta. Okay, so alpha, beta are what? 1, 2, 3. R, theta and phi. Can I write it? Can I write it like this thing? What will be g alpha beta? So g alpha beta will be 1 minus twice mu by r raised power minus 1, 0, 0, 0. So it is r square, 0, 0, 0, r square, sine square theta. Can I put just this very objective? Can I write? So now if you write g11, so it will be dx1, dx1. What is 1? It's r. So it is dr, dr, that is dr square. Clear? g11 is this thing. Now if I take 2, so it is dx2, dx2. That is d theta, that is d square. What is g22? It is r square. Then it is 3, alpha equal to 3, beta equal to 3. It is d phi square. It will be g33. g33 is r square, sine square theta. Clear? So now let's simplify it a bit. So which implies, so this is equal to 0. So it is something 1 minus twice mu by r. Okay, c square dt square, that's equal to, so this you have written it. Okay, so this is equal to, what that is equal to 1 minus twice mu by r raised power minus 1. Sorry, not. So this object is simply equal to g alpha beta dx alpha dt. Because this very thing I have written as g alpha beta. Clear? नहीं, मैंने नहीं लिखा Schwarzschild radius कहीं पे भी. So I have put actually Schwarzschild radius is actually twice mu. 2 times mu is Schwarzschild radius. Because mu is equal to gm by c square.
So what is this small r?
Huh?
2 mu by r. What is this r?
They are the same.
So you say r goes there.
Huh?
What is the difference? Where you get?
This is a radial coordinate. Okay, this is not the okay. One important point. There is a difference between two things.
one is actually the coordinate distance and another is a radial coordinate. Okay, so coordinate distance means, let's say I'm an observer, let's say, so let me remove it. So let me first clarify these two things. Suppose if I have, let's say, some mass m here, clear? So if I am taking, let's say, an observer O here, so let's say if I am having a distance d from this point to this point, so this is simply distance of separation between the two. It should not be confused with this r. This r does not mean the distance of separation between the two objects, clear? Got it? Wait a second. The distance, okay, so we call this simply as a radial coordinate. How you calculate now the distance between, let's say, between this O and this M, because it's in presence of this curved space geometry. So it will be given by, what is the distance coordinate? dr square. So it will be simply equal to, you multiply this element with what? This d. So the distance of separation between, let's say, this point and this point will be this object multiplied by this d. Got it? The way you are having the proper time and the coordinate time. How you calculate? Okay, let's forget this very object. How you calculate the proper time? So proper time is equal to this object. Clear? So this will be what? This is our coordinate time. Clear? Similarly, if you now calculate the length between the two things, so you will be having like this object multiplied by this thing. So one will be actually the proper length, what we call, that we call as a radial coordinate. Another will be actually the distance of separation between the two. Now,
Sir, अगर ये radial coordinate two से less than होगा, that means the signature of.
so we are not interested in r less than 2 mu. That I have just told you. We are only interested in r greater than 2 mu. So we are not interested in which region? R greater than 2 mu. The signature will be changed. So that I will tell when we will take the black holes. Okay. So when we will take the interior solution, then I will tell. For the time being, we are actually interested only in the exterior solution. We are looking at the space-time outside the Schwarzschild radius. Everybody got it? So there you should understand the meaning between these things. Right? So forget this thing. So if you have to calculate the proper time, so this object proper time will be this object multiplied by this thing. Eh? So this will give you the coordinate time. So now if you have actually the radial coordinate, you get the distance of separation between two observers, let's say, it will be something, this object multiplied by the proper length. So समझ आवा? Got it? Only in the Newtonian mechanics these will be the same thing. Let's take it. Okay, so let me give you the example. So let's take this object. First, you are having this proper time, let's say d tau. So that's 1 minus twice mu is twice gm by c square r. Then you are having dt, is it? So there will be actually rule kind of thing, is it? So it's a square. I have to take the root. Huh? So let's take c square tends to infinity. D tau and dt is same. We are not moving at the velocities, but when you take the Newtonian limit, you take c tends to infinity. Clear? So now if I am having the same thing, let's forget this thing and the other thing. So let's write our d, let's say dr. So call something other name. Let's say dx. So that's root of 1 minus twice mu by r. That is called minus 1 dr. Clear? So now what is the distance? So when you take c square tends to infinity, so what it will? So this term will go to 0. So it will be same thing. So that means geometry. It is same thing when you are on the surface. Let's think this way. When you are on the surface of the sphere, you try to measure the distance between the 2 points. How it will be? So if the distance between 2 points will not be simple, the Euler theorem. So root of x minus x1 square plus y minus 1 square. Clear? So it will not be the Euclidean geometry kind of thing. It will be described by how much curvature is there on the surface of the sphere. So समझ आवा? So that curvature effects, you can say, are inbuilt in these very factors. Clear? Everybody got it? Okay, so this is very important. Okay, so let's move. Okay, So this is our now g alpha beta dx alpha dx beta. Okay. So what we have, so let's write, so which implies 1 minus twice mu by r c square dt square. So that's equal to g alpha beta dx alpha dx. Okay. So this I can write as, let's take the root. Okay. So I will take dt. So that's equal to 1 by c, 1 minus twice mu by r raised power minus half g alpha beta dx alpha dx. So this I have taken on this side and then taken the root. Clear? So there will be root. So, or in other words, let's say I can write dt by some differentiation with respect to the parameter, dt by d sigma. Sigma is a parameter that's parameterizes the trajectory of the photon. Okay, we cannot parameterize the trajectory of the photon by the proper time. We describe the parameterize them by certain kind of parameters known as affine parameters. Okay, so forget about the word affine. So there exists a parameter. You simply think there exists a parameter which parameterize the trajectory of the photon. Clear? So let's call those kind of parameters to be sigma. One of sigma is there which parameterize this trajectory. Clear? So let's write it. So it will be simply 1 by c. So 1 minus twice mu by r raised power minus half. So it is something g alpha beta dx alpha by d sigma dx beta by d sigma raised power half. So it is actually d sigma square. So that will cancel with this d sigma. There is a root. Clear? समझ आवा? Now let's calculate this thing. Okay, so let's calculate the time. So you need to integrate this equation. Clear? So what this t gives me? Anybody? T gives me the coordinate time. Clear? So this dt is actually the coordinate time. Can anybody tell me what is the coordinate time? Coordinate time is te here and t plus delta e. If I am sending a signal at an interval of delta t, so that means the coordinate time for an emitter is what? Delta t. Clear? For sending two successive signals. And what is the coordinate time for this receiver? So it is delta tr for receiving the two successive signals. So समझ आवा? Everybody got it? Okay. So this I can write now. Let's integrate it. You take d sigma there. So you integrate. Let me integrate it from some te to tr dt. So that's equal to 1 by c integration. Let's say sigma e is the value at the when you are sending the signal. Okay. And sigma r is the value of the sigma when you are receiving the signal. So d sigma 1 minus twice mu by r raised power minus half. Okay, g alpha beta. So you can write this as x dot alpha x dot beta raised power half because these are x dots. Okay. Okay. So this I can write as tr minus t. So that's equal to 1 by c sigma e. Okay, so this I can write here. So this is same as tr minus t. Okay. Now what is this tr minus t? It is the difference of the coordinate times. So what is the coordinate time? For an observer at rest. So what I am having, this ds square will be simply equal to minus c square 1 minus twice mu by r dt square. Okay. So rest will be 0 because at observer at rest dr is equal to 0, d theta is equal to 0 and d phi is equal to 0 because they are all fixed. समझ आओ? Got it? So in other words, what is our proper time? Let's write proper time. So what will be that? So that's simply equal to ds square. Can anyone tell me? What will be that? What will be that? ds by c. Simply root of this thing. So what is that equal to?
So 1 minus twice mu by r raised for half. Clear? समझ आओ? Now this r is our radial coordinate. So I can write for emitter. So r is fixed. Clear? So what is our r? So it is at re. तो ये बात समझ? तो समझ आओ? So therefore, what I will be having d tau for emitter will be simply equal to 1 minus twice mu by re raised for half dt. समझ आओ? So now let's integrate this out. Okay, so let's integrate it along the trajectory. Okay, let's say from A to B for example. So since this is a constant, this does not depend on any variable because RE is now fixed. Clear? So समझ आओ? When you integrate it out, so which implies simply this delta like this thing. It's 1 minus mu by RE raised for half delta t. Difference between the coordinate times. Okay. So similarly for this for receiver, R is equal to RR, so which implies simply delta tau R is equal to 1 minus twice mu by RR and delta. Now you divide the two and use the factor delta T and delta T are same. Okay, so which implies this delta TE, tau E, delta tau R, that's equal to 1 minus twice mu by RE root. So it will clear? समझ आओ? So what is that equal to? Anybody? So it's 1 minus, what is twice mu? Tell me what is twice mu? It is gm by c square. Sorry, mu is equal to
gm by c square.
yes, twice mu is equal to gm by c square. Clear? No, mu is equal to gm by c square. Okay, so what will be this mu by re? Tell me. So it is gm by c square re. Anybody? So let's try minus times. So minus time. So it is simply phi re by c square. Because this is the potential. Gm by re minus times is the potential at the point re. Clear? So divided by c square. So therefore this I can write as twice phi re divided by c square divided by 1 minus twice phi rr by c square. Okay? This is, if you see, this is the formula we have already derived from the equivalence principle. Remember it? Okay? So I can write, since I can write the frequency proportional to 1 by proper time. Let's say if you consider as an electromagnetic wave with the frequency nu, then I can write this frequency in terms of the proper time as 1 by tau. Rather some factors, but it's inversely proportional tau. So which implies therefore, so this, so which implies then delta nu r, the received frequency by emitting frequency will be like this root of 1 minus twice phi at re by c square divided by 1 plus, sorry, 1 minus phi rr by c square. So you take it, so the received frequency, you get actually a shift in the what you receive, is it? A shift is by this amount. If you take c tends to infinity, let's say, so this will be 0, this is 0, it's 1. So in presence of the Newtonian gravity, there will be no shift. Clear? So we define now the gravitational redshift by this very formula. Okay, so the gravitational redshift. So gravitational redshift Z is defined as 1 plus Z is equal to something delta mu r by delta mu t raised to probably.
This is the formula. Nu r by nu e. So let me write. So what is the receiver frequency? What is the emitter bits ratio? And take it. So this is how we define what? Gravitational redshift. Z characterize the gravitational redshift. Okay, so what is Z therefore? So Z is equal to 1 minus mu r by. So this is a formula to characterize the gravitational redshift. Okay, so you can now have the flat space time here. So when this c square tends to infinity, let's say c tends to infinity, this is 0, you arrive at the Newtonian limit. So in Newtonian gravity there is no redshift. Clear? Any question? Any question? Okay. So let's move to the how much time is remaining? We'll be doing now the trajectory of a massive particles in the Schwarzschild geometry. Clear? समझ आओ? The way you are doing the Newtonian mechanics. Okay, what is the trajectory followed by a particle in the Newtonian gravity? It's simply the acceleration is equal to minus gm by r square. The acceleration due to gravity. Clear? So that is how we calculate the trajectory. But we'll see, we'll recover this result in this geometry as well. Okay, before doing that, so let's look at the Lagrangian. So you are having Lagrangian for a free particle, or let's say Lagrangian. So you write like this thing: m by 2 x dot square plus y dot square plus z dot square minus v r. Okay. This is the Lagrangian for a particle moving in a potential v. So can I write? Okay, let's forget about. Okay, so you are having this m by 2. Let's write this m by 2. So let me write this as something eta alpha beta. Can I write it as x dot alpha, x dot beta? Can I write it? Minus v of r, where eta alpha beta it's equal to 1, 1, 1, and rest are 0. Can I write it? Can I write it? Can I write it? Simply just take the sum. There is a sum or alpha and beta. Just look, you retain the same thing. So that means in the okay, so I can put it in this very fashion. So this can be generalized to the curved space time. In the curved space time, therefore I can write, okay, so I can write this Lagrangian. So this I can write for the timing m by 2 some g alpha beta, because in the curved space time this eta alpha beta generalizes to what? G. Clear? So I write it as something x dot alpha some x dot beta minus via r. So sorry, let me write now ij, because we are having a time component as well. समझ आओ? Where I and j goes from where? 0, 1, 2, 3. Okay. समझ आओ? But if you look in the gravity, so the equations of motion are independent of the mass of the particle, test particle. Clear? So you are having mx double dot is equal to minus g capital M small m by r square. You can cancel the mass on the left and right hand sides. The equivalence principle. So that means you don't require actually m here. समझ में what you are having a factor half. So that you can absorb this half. You can ignore. So in other words, in you can have now the Lagrangian for a particle in the general curved space time. So like this, x dot I, x dot g. So it is only the free particle. So let's take this free particle. Then you are having a potential. Let's say v of r. Let's forget about the potential. So this will be simply what? Our free particle. So the Lagrangian for free particle. So home assignment will, okay. So what are the equations of motion? Those are the Euler equations. Clear? So here the dot is not with respect to the t. So here the dot was with respect to t. So this x dot means in flat space time dx by dt. Simply the derivative of position with respect to time. Here this derivative is with respect to this x dot I is simply dxi by some d sigma, where sigma is some parameter which characterize the curve. Okay, it can be the proper time. Huh? समझ आवा? So, clear? So what I was saying? Huh? Okay, so now what is the, okay, how you describe the equation of motion in this very case, in the flat space time? So simply d by dt partial L by some partial q dot minus partial L by partial q is equal to, is this the way you describe the equation of motion? Now here you describe the equation of motion by d sigma, since this t goes, since it is the time here, because time is absolute in that very concept, so you are having now a parameter sigma, clear? Which can be, now you can replace the sigma by the proper time, clear? So then you are having this partial L by partial this x dot I minus partial L by partial xi is equal to 0. So how many equations are there? I goes from 0, 1, 2 and 3. So this is our, what is this x dot? This x dot is d sigma dx by d sigma. So now this is our Euler equation. Okay, in the curved space-time background. You got it? Okay, so this is a very general equation. From this equation, calculate the geodesic equation. What you need to calculate? So geodesic equation we calculate from the variation of the action, clear? So now look at the mechanics. If you are having action given, you make the variation, you get the Euler equations, clear? But if you know the Euler equation and the Lagrangian, you can calculate the equation of motion. Now here I am giving you the Lagrangian as well as the equation of motion Euler equation, is it? So what you can calculate? The equation of motion. So you need to substitute. Okay, so let's write. So let me tell you. So what is partial L by partial x dot I? So let's write this as partial by partial x dot I. So this will be G A B x dot A x dot B. So there is a differentiation with respect to dots. Okay. So what that will be? So y G A B, then x dot. Let's say x dot A. Then what it will be? Delta B I. So it will be something to y G A I x dot A kind of. Okay. So rest will be, you have to define now differentiation with respect to what? Okay. So make now the differentiation with partial L by partial L. So you have to differentiate everything here. Samajh aawa? You got it? So you differentiate with, now you have to differentiate GI with respect to XI. Samajh aawa? Just do it at your places. Huh? So this will be the home assignment here. Calculate geodesic equation. From here. So because this will be now used, this equation will be used heavily. So let's stop then. Okay, by the way,